Okay, yeah, so let me introduce the speaker for today. So today we're happy to have Eugene Gorsky from UC Davis to talk about Zergel bimodules and Hilbert schemes.
All right, thank you so much for inviting me. So I think I'll switch off my video for better connection, but I'll write on the screen, and if you have any questions, please stop me anytime. So I will be speaking about Zergel bimodules and Hilbert schemes, and I will define all these things in the talk. And this is based on series of joint works with Andrei Negut, Jacob Rasmussen, Matt Hogenkamp, Paul Wedrich, and other people. But I think today I will speak just about joint works with these guys. So let me start with some motivation. So the motivation comes from the Hecke algebra. So this is the algebra generated by elements T1 through Tn minus 1 with relations that Ti plus 1, Ti is Ti plus 1, Ti plus 1, Ti Tj is equal to Tj Ti if I minus j are far apart. And then you have a quadratic relation which says that Ti minus q, Ti plus 1 is equal to 0. So if you're a topologist, you can think of it as some kind of Braid's modulus Kane relations. So this is the same thing as Braid's on n strands modulus Kane relations. And in this presentation, Ti corresponds to the positive crossing between I and I plus first strand. So I have n strands, and I and I plus first are crossed. And Ti inverse corresponds to the negative crossing. And so this relation over here and this relation are not just Braid relations. And this quadratic relation you can think of as some kind of skein relation or some linear equation connecting Ti and Ti inverse. So maybe I don't want to write it precisely, but let me just say that this is just a skein relation between positive crossing, which is Ti, negative crossing, which is Ti inverse, and identity, which is just one. So you can write it as a linear relation between them, and that's the Hecke algebra. So we will be interested in some structures related to Hecke algebra and some interesting elements in it. And so one class of interesting elements are called Jussius-Murphy elements. Which are obtained as following. So you take I strand, move it around like this, and then move it up like this. So let's call it Li. So you can write it as a product of elementary crossings, and this will be some product of Ti's in the Hecke algebra, but I would really think about it as an element in the Braid group. And so the important property of these Li's is that Li-Lj is equal to Lj-Li for all I and j. And so L1 through Ln generate a commutative subalgebra in the Hecke algebra. And this is in fact maximal commutative subalgebra. And one more element which I will be very interested in is the full twist. So it's again a braid, which you can think about, let's call it F. Either you take this braid on n strands and raise it to power n. So you can think of your strands wrapping around each time and rotating 360 degrees. Or you can actually write it as a product of these LIs. So this is equivalent, that this is a product of elementary twists, which are these Drusus-Murphy elements. And so the fact that we will need as a motivation. So first of all, the full twist is central in the braid group. And its image in the Hecke algebra is also central. And all the powers of it are central as well. So in general, it's an important fact that the center of the Hecke algebra is the same as symmetric functions in L1, using this script, L1 through Ln. So in particular, I can take the sum of L's, I can take the product of L's, which is F, but all symmetric functions in L1 through Ln will be central. They will satisfy some relations, so there are more symmetric functions than elements in the center, but at least they generate. So this is the center of Hn. And so in particular, we can think of the picture where we have the center of Hn. It embeds into this commutative algebra generated by L1 Ln. And then that embeds into the Hecke algebra. So these are just inclusions, which are homomorphisms. And we can look at the projections, which are joined to inclusions or composed projections, maybe. So projections, for example, from Hn. So most important projection will be from Hn to the center, are adjoint to inclusions. With respect to some non-degenerate bilinear form. On Hn. So that's one way to phrase this, and we will be interested in categorification of all these maps. What is the categorification of the center? What's categorification of Li? What's categorification of the Hecke algebra? I'll try to explain this in details. And another thing which is good to know is that we can look at the cocenter, which is a fancy name for just the quotient of Hecke algebra mod the commutator. And as a topologist, you would really think about it as closed braids, mod-skein relations. So what does it mean? So at X I'm braid beta, I close it up, and I close it up, let's say, in the annulus, and then I'm allowed to perform skein relations. So in particular, in the annulus, I know that if I have alpha and beta here, this is equivalent to putting beta here and alpha here. Because I can slide alpha through the top to the bottom, and it will be oriented exactly the same way. And so in particular, we can say that the closure of alpha beta is the same as the closure of beta alpha. And so in particular, this is this commutator relation. So somehow when we take the quotient of the Hecke algebra on this, we can think that we just identify alpha beta and beta alpha. And this is what it is. And the scaling relation will happen locally on beta. And then the important fact is that it's proven by many people. Let me refer to derive that Hn mod Hn is isomorphic to symmetric functions of degree n. And there is a basis. So there are various interesting bases in symmetric functions, which you can draw as certain braids in the annulus. And very concretely, we can use it to define link invariance.
Can I interrupt with a question?
Yeah, sure.
I think, I mean, there's something bothering me here. You're just saying that making, I know you're not quite saying this, but it sounds like you're saying making things commute is the same as making the braid close. But braid closure is just allowing you to cyclically permute the element, the letters in a word.
Yes, but this is the same. I mean, because this is, so what is the quotient by commutator? Basically, you're saying that your quotient by alpha beta minus beta alpha.
Oh, I'm not making the transition from groups to algebras. That's my problem.
No, this is the algebra setting. That's the point.
Yeah, no, I realize that. That was my confusion. I think I understand.
So you need to quotient somehow by ideal generated by, yeah, and then that's fine.
Thank you.
And maybe like more important point, so I'm saying braid closure, so it might be confusing. So I'm really talking about like annular braid closure. So this means that so sometimes you talk about the link as a braid closure. So it's not a link in S3 so far. It's just a link when in the annulus, when I take some point out, so I'm not allowed to move the loops through. Not allowed to change the number of strands. I'm just allowing to conjugate in the braid, and that's basically all. Okay. All right. So, and then just want to say that you can define link invariance this way by saying that first you take a braid, then you project to this quotient, and you get the symmetric function, and then you basically evaluate symmetric function at some point. So this is evaluation. Of symmetric function at some point. And so link invariance, which you can obtain this way. So for example, I wrote Q and A, you can get Homfly polynomial, you can get Jones polynomial. So I think in one of the papers of Jones, there is a very clear explanation how you actually do this. So you take beta, you project it to the quotient, which you can identify with symmetric functions of degree n, and you just evaluate this, you get Homfly polynomial. You can also phrase it in terms of representation theory of Hecke algebras, but maybe I don't want to introduce more notations not to confuse everyone. And secretly, there is some duality between the center and cocenter, which I might discuss later, but I think all this is fairly relatively known. And so we can study the center of the Hecke algebra, we can study cocenter, which I prefer to visualize like this. And then the goal for today, which I would write in blue for today, is to categorize all this. And there will be some connection to the Hilbert schemes, but let me see it in a second. All right, so any more questions about the Hecke algebra and center cocenter? Good.
Wait, so there's a question in the room.
So it recovers like the Jones and the Homfly polynomial. Do you think a specific point to evaluate it?
So the question is, in order to get the Jones and Homfly polynomial, do you evaluate this at specific points, so probably specific parameters?
Yeah, so you have a symmetric function, and for Jones, you just evaluate it basically at 1 and q, and the rest of the variables are 0 in some normalization. And then for Homefly, you can phrase it slightly different. So yeah, maybe I should write it down to make it more clear. So here you evaluate, so example of evaluation, which is very important, is that you have a symmetric function in here, and you go to f of 1 q to the n minus 1 when n is some number. And if n is 2, you recover just the Jones polynomial.
Okay, yes. So the person is happy.
Yeah, okay, good. Everyone's happy. All right, so then we move on. So first of all, I'd like to start from the end. So what is the categorification of the Hecke algebra and the Homefly polynomial? So this is done by Zorgel by modules.
I'm sorry, I actually did have one other question that occurs to me. So lambda n is a symmetric functions in n variables? You say degree n, but do you mean n variables?
No, infinitely many variables.
Degree n and infinitely many variables. And then what is that a, then this evaluation, what is a? I mean, is a the point you're evaluating? You're talking about CQA. I don't quite understand what a is there.
I mean, so here I can evaluate at this point. So even if I have a function in infinitely many variables, I can just put zeros in the end. So there is no a here. And if I want a,
there's, you say CQA.
Yeah, exactly. So this would give you Jones. So if you have a, then you say that f expand it in power sums. So expand f in power sums pk, and then replace pk by something like 1 minus a to the k over 1 minus q to the k.
Okay.
So this is kind of evaluation, but not exactly. So you can think of it as a limit of this procedure. So if you evaluate a function at 1q up to q to the n minus 1, then power sum will be something like 1 minus q to the nk over q to the k. And so the relation between this and this will be a is q to the n. So power sum evaluated at this sequence 1q up to q to the n minus 1 is precisely this rational function when a is q to the n.
Okay.
And you can do it more or less formally. So I think the key emphasis that I want to make here is that if you are at this stage, if you already get a symmetric function, it's really easy. It's some easy algebraic combinatorial procedure that everyone can do. Somehow, given a braid how to compute this symmetric function, that's slightly more subtle, but abstractly we know that this is possible. Okay?
Okay.
Good. All right, so good by modules. So we start from the ring R, which is polynomials in n variables. And we have BI, which is polynomials in 2n variables. Modular relation that xi plus xi prime, sorry, xi plus 1 is xi prime, is xi plus 1 prime, xi plus 1 is equal to xi prime, xi plus 1 prime, and xj is equal to xj prime for j is not equal to I and I plus 1. So this is a very concrete description. Less concrete description is that you take R, you tensor with R over the ring of invariants under transposition I and I plus 1. So this function xi plus 1 and xi plus 1 and xj, they're all symmetric under this transposition of I and I plus 1. And I'm saying that this is one copy of R, another copy of R, and you tensor over invariants under this. So this is slightly more abstract. This is very, very concrete thing. And this is an RR bimodule. And let me just define it and maybe. So the category of Zorgel bimodules So this is the full subcategory of RR bimodules generated by BI under direct sums, tensor products, and direct summands. Okay, and so typical object will be direct summand in some tensor product of BIs. So typical object is a direct summand in BI1, BI2, BIR. And the big theorem of Zorgel says that this is a clarification of the Heike algebra, in particular, the Grodny group of SBMN is the Heike algebra. So SBMN categorifies HN. And this is pretty hard theorem. We'll need actually something easier. So we'll need complexes which are of the following form: Ti Bi to R, and Ti inverse is R to Bi, where there are some maps which I don't want to specify, and the theorem of Rukia says that Ti and Ti inverse satisfy braid relations up to homotopy. That is, you take Ti, for example, a tensor with Ti inverse. That will be a 4-term complex, but it's actually homotopy equivalent to just R, which is kind of identity. Then Ti, tensor Ti plus 1, tensor Ti is the same as Ti plus 1, Ti plus 1, and so on. So they satisfy braid relations up to homotopy. And then maybe last abstract thing which I want to see is if you have a braid beta, so you can associate to it a complex T beta. This is a complex of Zorgel bimodules. Obtained by tensoring Ti and Ti inverse. And this is a well-defined complex up to homotopy. And so you can use it to define Kavan-Frazansky or Hom-Fly-Petit homology. Or Kavan-Frazansky. So this is just Hom from identity to this T beta. And strictly speaking, take homology of that. So this is a complex of Zorgel bimodules. If you have Hom from identity to T beta, it's a complex of R modules, and then you take homology of that. So this is a fairly concrete definition. Maybe I want to say a topological remark for people who've seen, for example, Kavanagh homology, and this sounds all too algebraic and abstract. This is actually not so bad. So Bi in diagrammatic language, this is the following thing. So you take n strands, and you take i's and I plus first strand. So here you have variables x1, xi plus 1 to xn. Here we have variables x1 prime, xi prime, xi plus 1 prime, up to xn prime. And then if you look at the definition of bi, so what happens is that we have these variables I and I plus 1. They kind of merge together and they split, but we don't know if they're the same or permuted, because somehow we know that the symmetric functions in xi and xi plus 1 are the same, but you don't know what happens to them. And this is drawn like this thick edge of multiplicity 2. And then Ti is just the complex where we have this thick edge and it goes to identity. And Ti inverse is this thick edge, and identity goes to thick edge. And so basically in the definition of T beta, you take any crossing, you resolve it either like this or like this, respectively for Ti and Ti inverse. And then you have a giant complex made out of products of BIs, and then you take home. So that is basically the definition of Zorger bimodals, and this is the codification of Hecke algebras and TIs and things like this. But it's so far it sounds very abstract, and it is abstract. Okay, so any questions so far? Good. So then I want to do some computation. So I want to say something like very, very concrete about this Zorger bimodals and compute it. And I want to talk about the full twist braid. So again, recall that F was this braid. And so theorem 1, I'm looking at the theorem, myself and Hogenkamp, which was conjectured by myself, Nigwood, and Rasmussen. Let me not write this. So for k greater than or equal to 0, we have home from identity to full twist to the power k is j to the k mod y, j to the k, where g is the following thing. So this is an ideal in polynomials in x1 through xn and y1 through yn. So y's didn't appear before. And so you take this ideal generated by xi minus xj and yi minus yj, and intersect all these ideals for all different I and j. This will be j. Then you take k's power of this ideal, mod y times j's power, and this recovers the homology of the powers of the full twist. So it's interesting that by definition, if you think about it, so homology of the full twist is naturally an R module. So it's naturally a module over polynomials in x1, xn, which is R. And the right-hand side is also naturally a module over R, and the module structure agrees. But to describe this module over R, you need to introduce these additional y variables and then kill them by killing the maximal ideal in y's. So here y is the maximal ideal generated by y1 through yn. So maybe I want to give an example for this not to be super abstract. So for n is equal to 2, we have j, and just ideal generated by x1 minus x2, y1 minus y2, inside C of x1, x2, y1, y2. And then we can write it by generators and relations by saying, let's say, call it this guy alpha and beta. So we have two generators, and alpha times y1 minus y2 is beta x1 minus x2. And so j mod yj. This is generated again by alpha and beta, now over x. And the only relation is that beta times x1 minus x2 is equal to 0. So you have a free copy of C of x1, x2 generated by alpha, and you have another piece, which is this beta modular relation that beta times x1 minus x2 is equal to 0. And this actually matches the computation that you could do with ordered bimodules. But maybe for the interest of time, I won't do it, but I want to say this is something concrete in this case that you can check, and you can see all the gradings from it. You can see how x1, x2, x. So this is something very concrete, and in the end, like if this is the definition of Hohenfeld homology, you can interpret it as just we computed Kavan-Frazansky homology of the powers of the full twist this way. So this is some concrete computation, not homology. Now, why do we care? So this is the next part. The Hilbert schemes. So what is the Hilbert scheme of points? So we have Hilbert scheme of n points on C2. This is the space of ideals I inside C of xy. Just one x and one y in this case, such that the dimension of C of xy mod I is equal to n. So this is the Hilbert scheme of n points on C2. And it's very nice. So the fact is that, for example, the theorem of Gorsky. So Hilbert C2 is smooth. Dimension is equal to 2n. And we have a Hilbert-Cho map from Hilbert scheme of n points on C2 to Sn of C2, which sends the ideal to its support. So it will be a bunch of points on the plane with multiplicity. So number points in C2 with multiplicities. And then we can do the following weird construction. So we have this map Hilbert C2 to Sn C2 xn. So we'll also have projection from C2 to the n to Sn C2. And then we can form the fiber product. And for experts, I need to say that this is reduced fiber product. And
what is X here? I'm sorry, I lost
that. So that's the definition of X. So you have the Hilbert scheme. It projects to symmetric power. You have n's Cartesian power of C2. It also projects to symmetric power. And then I just take fiber product of them with reduced scheme structure. So this is called isospectral Hilbert scheme. And it was defined by Heyman. And now the key fact is the theorem of Heyman. So there are several things here, but let me just mention one for, again, the interest of time. Is that Xn is actually the blow up of C2 to the n along the union of all diagonals. So C2 to n is the space of n tuples of points on C2. So I have codimension 2 diagonals where 2 of the points collide. So these are, let me not write it, but there are where 2 of the points collide, they do have codimension 2. And now what is the diagonal? So it's given by equations xi is equal to xg and yi is equal to yj for some I not equal to j. And so in particular, the ideal defining diagonal is just ideal generated by these things. And so ideal defining the union is the intersection of these ideals. And so in particular, we can rephrase, and this is our ideal J, which already appeared in the theorem. So this is same ideal as above. So above it, I stated, let's take this ideal. But geometric meaning is that this is ideal defining the union of all diagonals in C2 to the n. And then this theorem of Heyman, if you want to do it more algebraically, you can say that xn is just the proj of the direct sum of from k is equal to 0 to infinity of j to the k. And so then there is a construction how to get from, how to relate the two things, how to relate the Hecke category, the sorted bimodules, and the Hilbert scheme. So construction. Relating SBMN and Hilbert. So this is myself, Nigut, and Rasmussen, model of that theorem, whatever. So the construction is very easy. So you start from A, which is a complex of Zorgli bimodules. Then we can define the following thing. Direct sum of homes from identity to A times the full twist to the k. So this is a graded module over the graded algebra. Direct sum from k is equal to 0 to infinity home identity to f to the k. But this graded algebra, we just computed it. It just direct sum from k is equal to 0 to infinity of j to the k mod yj to the k by the theorem. And so in particular, it's a module over this. So it's a module over just the direct sum of j to the k. And so as a result, we can construct it and get a sheaf quite coherent, let's see. Sheaf on the proj of direct sum k is equal to 0 to infinity of j to the k, which is this space xm. And so after this, we project to Hilbert. And we get a sheaf on Hilbert. And so this is some abstract procedure, which I try to outline here, but the point is that we start with a complex of Zorgli bimodules, or in particular, we can start from a braid, produce a complex of Zorgli bimodules by a procedure, so or a braid. and then run this machinery and get a sheaf on the Hilbert scheme of points. So it's corollary. We give him a braid beta on n strands. We obtain a sheaf. Let's call it f beta on Hilbert of C2. And so in particular, we can check that if I start from a braid, add a full twist, this corresponds to the fact that I get the sheaf f beta and just tensor with a line bundle of 1 on the Hilbert scheme. So adding a full twist to a braid corresponds to tensoring with a line bundle. On Hilbert C2. And in many cases, we can actually identify this sheaf explicitly and use algebraic geometry or Hilbert scheme. So we can use, let me write it carefully. Phi f beta for many braids beta and use algebraic geometry of Hilbert C2 to identify say to compute equivalent homology of beta. Okay, and so this is the key construction that we have. So the problem, which is very open as far as I know, so problem is to extend it to a well-defined TG functor. So secretly, I don't want to go into any homological algebra details, but we have a homotopy category of complexes of surrogate bimodules. We have derived category of Hilbert scheme, and somehow extend this to a DG functor between homotopy category of SBMN and derived category of Hilbert C2. So there are many subtleties here which I don't want to go, but I think the idea and the construction is now more or less clear. And so I think I have 5 minutes, so I want to say something else. So maybe I want to say one more conjecture before going on. So conjecture, which is kind of optimistic, I would say. But based on what we know about the Hilbert scheme, it's not so bad, is that the Drinfeld center, or I would say categorical center, of SBMN, or homotopy category of SBMN, is generated by powers of the full twist and their direct summands, undertaking cones and direct summands. And this corresponds to the fact that the derived category of the Hilbert scheme you can get by taking powers of O of 1 and cones and direct summands, and that is well known in algebraic geometry. But this tells us something completely separate from the Hilbert scheme in some sense. We just want to understand what is this center of the Hecke category, which would categorify the center of the Hecke algebra. And then in last 3 minutes, I just want to say something about the cocenter. So I don't really have time, but let me just say it. So derived trace, or let's say just categorical trace. Cocenter. So I can just say that there is a category. So this is a category generated by annular break closures, which appeared before. That's why I wanted to kind of go here. And there are some objects, there are some morphisms. Definition is actually quite involved, but roughly speaking, we take again Zorgil bimodule and close it up in some categorical sense. And what I want to say is the theorem of myself, Hogenkamp, and Wedrich is that first of all, the trace of SBMN is generated by the trace of identity and its direct summons. And B, so to understand this trace properly, we need to know the morphisms of trace of identity. This is the same as Hochschild homology of the category SBMN. And this is the semi-direct product of this algebra, semi-direct Sn. So these are even variables and these are odd. And so for people who think about these things, so again, this is some version of this category of annular links with some categorified version of annular links in some cells. So this is related to annular link homology, which was studied by many people, including Melissa here. So this is related to annular link homology. And then maybe one more thing which I want to say is that remark is that geometrically this trace category is supposed to be related, but there is like roughly equivalent, I don't know how to say it properly, to the category of character shifts. And TRF 1 correspond to the Springer shift. And so, for example, without thetas, this endomorphism ring of Springer shift with X's and Sn, it appeared in the work of Lowrider and several other people. And it is expected that this is related to the work of character shifts. So compare, let me just say compare and we're done. So compare with the work of Lowrider and recent work of Bezrukavnikov and Tolmachov. Where they make it slightly more precise and concrete. So I think I'll stop here.
Okay, thank you very much. Are there any questions?
Can I have a naive question? So the fact that you pass through the isospectral Hilbert scheme and then back to the original Hilbert scheme, it looks like you start with some kind of order tuple back to unordered tuple.
In some sense, yes. So if you have, maybe let me scroll up. Yeah, so here, like, if you just look at the support, so you have n points on C2, they're ordered, and this happens here. Here, they're unordered, and so if the points are distinct, that's the only difference. So the ideal defining n distinct unordered points is uniquely determined by these points, and we just order these points. So this is n factorial to 1 map. And then the hard part of Heyman's work is how to extend it to the locus where the points collide.
Right, so I mean, completely heuristically, so the Bray group, if you symmetrize, then it becomes just symmetric group, right? Yeah, so I mean, a lot of non-commutative information of the Bray group would just vanish. So I mean, what do you obtain from this procedure compared to when you start with the Bray group and symmetrize it and then apply a similar procedure to directly go to Hilbert scheme?
So this doesn't really work for not homology, this symmetrization, as far as I know. No, somehow this symmetrization, like one way to think about it is that you have a braid closure, and you can cut it somewhere here and say that you have some variable x1 here, x2 here, x3 here, and you have this x1, x2, and x3. They define basically coordinate of a point on the Hilbert scheme, although I'm lying a little bit. And the point is that if you cut it here, or if you cut it somewhere in the middle of beta, you get different results because your variables get permuted, and somehow symmetric functions in x1, x2, and x3, they're all the same, but it's the order of the points you can't really remember. But again, the hard part is like how to get this y's, and the y's I didn't really explain, but they also appear in this picture, and then you need to permute both x's and y's.
Okay, yeah, thanks.
I don't know, it's a good answer.
Yeah, maybe it's not a good question, maybe. And another thing is that the Li that you mentioned in the beginning of your talk, can I see the definition again? So this is Juicy-Murphy elements, right? Mm-hmm. So it seems to me that this will generate a whole pure group, but you're saying this generates a...
No, not necessarily. They generate a commutative subgroup. So if you, for example, I mean, you can think of second and third strand wrapping around each other twice. And so this will be pure braid, but it's not a product of these guys. So these guys, I mean, it's easy to see that they commute because somehow Li commutes with anything on smaller number of strands, right? On less than I strands, because you can move it through this loop. And so in particular, if you have I less than J, then you have Li kind of inside Lj, and you can move it through, and they easily commute. So it's easy to see that they commute.
Yeah, from what I see, so if you have Li and Li plus 1, then the Li plus 1 down there will not be able to cross this Li, right? Maybe
it really cross, it kind of goes around.
Oh, okay. Okay. So it doesn't play anything, any role in your theory except for defining the full twist?
It does, but I didn't have time to say it. Yeah, sorry. So you can look like, so here I try to outline the relation between the center and the full twist to the Hilbert scheme. So there is analogous story. So our original motivation was to understand this Li. So maybe let me write one sentence, because since you asked, then I didn't write where Li's are. So just say, so you have this kind of subcategory generated by powers of F. It sits inside whatever generated by Li. and it sits inside HN. So these correspond to Zorgil bimodules. This, roughly speaking, by this work corresponds to Hilbert scheme on C2, and this corresponds to flag Hilbert scheme. So this is the flag Hilbert scheme, and the space of flags when I have C of xy, some ideal, some other ideal, some other ideal. And so on this thing, you have a bunch of line bundles, Li, which is I. Okay. IK, and so again, they should correspond to Drusius Murphy elements.
So when you say,
but I didn't really say it, and sorry, I didn't have time to explain. But you can look at our paper with Nigur and Rasmussen, and we had long discussion like why they should correspond to LK, why, for example, any product of these line bundles correspond to product of UC Murphy elements, and many other things. In particular, you have the sum of LIs. That's an interesting central element in the Hecke algebra, and that corresponds to some rank n vector bundle in either of this picture because it's filtered by the small line bundles. But again, yeah, sorry, I didn't have time for that.
Okay, any more questions?
Hi, I have a question. It's also related to the Drusius Murphy elements. Are there elements for the cocenter that play like a similar role, or just interesting?
There are operators on cocenters, so you can. So I think the closest thing that I know is that you can. So here is your braid closure. So you can take some extra braid and then wrap it around, and then do it like this. So you can. So you have an operator on cocenter, which goes from cocenter of Hecke to Hecke n+1, which just adds a circle. But you can add this circle and wrap it around, and maybe you can wrap it around several times.
Mm-hmm.
So this gives an interesting operator from this kind of cocenter of Hn to cocenter of Hn+1. And you can study all these operators. So they form, topologically, they form the skein algebra of the torus somehow, because you can draw them on the torus around it. And algebraically, they should form some really interesting kind of induction restriction thing, and they should be related to elliptic-wall algebra and other things. But I think that's the closest thing. And you can also kind of add two strands at once. So you can kind of add this thing, and then you add one even more thing. And yeah, so you should have interesting kind of twisted inductions.
Okay, cool. Thanks.
Okay, any more questions?
Yeah, so this is a long shot, but I really want to be able to see this visually. Like if you give me the quasi-coherent sheaf on the Hilbert space on C2, is there some way of like projecting to one of the C1s and then looking at like I don't know, like this is probably really hard, but there's some theory for like Legendrian knots where you can try to come up with a sheaf corresponding to a Legendrian diagram. Of course, you have to have it on a plane, so it probably has to be C2.
No. That's very different thing. That's related, okay. But it's very different picture. So that's like a constructible sheaf. There's a coherent sheaf, first of all.
I'm sorry. Yeah.
And so the diagram picture, you can phrase all this. So so these Zorgil bimodules, you can interpret as some kind of space. So Pi, it's homology of some space. And what is the space? So you take the space of full flags in Cn. One here. let's call this, I don't know, flags N. And you have flags N cross flag N. And inside you have a locus where all flags but i's are the same. All subspaces are the same. So here we have f1 up to fn minus 1. Here we have f1 prime to fn minus 1 prime. And here we have the locus where fj is equal to fj prime for j not equal to I. And so if you take homology of this space, you get bi. And this is not so hard to prove. If you want ti, you actually require, so this corresponds to pi. And you can also inside, you can look at this minus diagonal where you say that fj is equal to fj prime for j not equal to I. And fj is not equal to fj prime. Fi is not equal to fi prime. So this, roughly speaking, corresponds to Ti. And then you can interpret this Kavan-Franzanski homology as homology of some space built out of these flags. And this will be like bigger but Samuelson varieties built out of this. And you can interpret Kavan-Franzanski homology from there. And from there, there is a link to constructible sheaves. But as far as I know, it's completely unrelated to Hilbert scheme. So there are just two different perspectives in some sense.
So homology here is some equivariant homology.
Yeah. You can take it equivariantly. Mm-hmm.
Okay, so it's not just singular homology.
And here you can just take homology because your axis will be like Chern class of line bonds here.
Okay.
Yeah. So this was the original motivation of Zorgel, which I also didn't explain.
Okay, any more questions? Okay, it doesn't seem to be the case. So yeah, let's thank Eugene again.
All right, thanks so much for having me. So do you need this